Hi, welcome to New Electromagnetism Applications number 12. In this video we're going to discuss IBM's Camel Back effect announcement. IBM recently announced a new electromagnetic effect that they call the Camel Back Potential. Here's the link to it. If I remember, I'll put it in the low bar, but I never remember to. I apologize. And they claim it's an effect that's not accounted for in Maxwell's 4 equations. Now, here's the problem with that. This statement is right, but they're making the assumption that Maxwell's 4 equations are the complete antithesis, or the complete encompassing of all known electromagnetic effects. Now, I'm not talking in terms of new electromagnetism or anything. I'm talking in terms of an expert. I'm an expert in classical electromagnetic theory. And I'm telling you right now, Maxwell's 4 equations are not the complete embodiment of known classical effects. That's a myth that's being perpetrated among college graduates. And we'll cover that in a little while. And I'm going to show you that the effect that is presented in this thing is in fact covered by known existing classical models, and that this isn't a big deal. What I am going to show you, though, there is a silver lining that they're ignoring. That's going to be cool. So, their claim. This is their own words. The IBM research team recently discovered a subtle hidden feature in electromagnetism, a previously unknown field confinement effect. Oh, they love these big $50 words. Looks like they're getting coaching from Ken Wheeler, that we've named the Camel Back effect. And basically what it is, using a poor picture here, is they've got two magnets, bar-shaped magnets. They're not bar magnets, they're actually flat magnets that have rounded edges. And they got a little piece of graphite in the middle, and what happens is they move it to the edge, it rotates back to the middle. They move it to the edge, it floats back to the middle, and it stays right there. And so they got this little potential here that looks something like this. It's kind of drawn at an off, something like that right in there. That's that little blue graph. That's the graph of the potential that they're calling it. Okay, so let's discuss this. I was initially elated by this because, as you guys recall, that when I was doing, here's the little railgun proof of concept section, POC, proof of concept, and that I showed demonstration that works pretty good. Then the problem with it was in the physics modeling, here's a current ring that simulates the edge currents of the magnet. That's in the new model of magnetism. I'll show you the video link to that in a minute. And it shows very clearly that you can model a magnet simply as a current ring. And here's a little armature that would go in this little track. And the problem I was getting with the physics, it said when this thing, armature, is traveling at 300 meters per second, which would be the speed of a bullet, I get virtually no back EMF generated in the armature. So there's something wrong. Okay, and I was hoping that these guys came across something so I didn't have to do the work and figure it out on my own. I was just really hoping for that. Okay, and then this anomaly that it was in the railgun project, that's why the railgun project was put on hold, and that's the reason why we went back and hunt for all known anomalies. By resurrecting the paradox experiments, developing the edge current distribution, the thing I kind of ignored, but now I'm thinking maybe that has something to do with it. And the completion of Vortrix algebra, which fixes the anomalies in math, and I think this is going to be the big payout here because it's showing me things that are pretty interesting. For those who are following on the Patreon side, you know where we're going with that. Okay, but let's get back. What is new electromagnetism? Okay, now what I'm trying to do here, I'm not trying to, this is probably not a good thing to do here right now, but I'm going to do this anyway. New electromagnetism is my way of accounting for all known electromagnetic, because here's what they're saying. They're saying that they have a new effect that isn't accounted for with classical theory. And what I've done with new electromagnetism, I said, listen, charges are the most fundamental building block of electromagnetism. All we can do with humans, all we can do is make a charge do something and watch how it affects another charge. We really do not have a good grasp of what goes on in between. And so what I've done with new electromagnetism is catalog all the charge-to-charge effects. Here's Coulomb's model. I got a big check mark here. I'm pretty good. That's good. Down here is new induction, which I found through experimental, and you can go find all that data in the Foundation series. This replaces Faraday's law. Faraday's law is ambiguous. Faraday's law violates 17th rule of acquisition. It's ambiguous. And so, but that's not these aren't the models that are being used here. This is a completely magnetic field phenomenon. And so new magnetism is the three middle terms of new electromagnetism. Now these outer two terms here are derived directly from F equals QV cross B, classical theory. This middle term here I had to infer from two different means that there has to be something else here. But one thing that I'm not sure about is what I did the same flaw that classical theorists did. I found the one model that worked and didn't bother to find any others. And I'm thinking that might be my problem right there. Okay, but you know, that's this different subject. What I'm trying to show you here is that I'm going to show you that this Camelback effect can be computed completely from these two models of new electromagnetism, which is F equals QV cross B. And F equals QV cross B is not part of Maxwell's equations. Yes, it's not part of Maxwell's equations. Now let me just do something here for you. In one of the, and for the Patreon side, I released the vortex diagram of classical new magnetism, and showed that this is the area. This is a moving charge, and the field effects before and after moving charge are the parts that are unknown, that are having problems with. The area out to the transverse side, we get good results with. Okay, these transverse region, we have very high confidence. Pretty much everything we do out here works well, works right. This is stuff in here that's difficult to measure. That's where we're getting the anomalies that we're chasing after with the new electromagnetism initiative that we're doing right now. So unfortunately, when I looked at their experiment, they're all operating in the transverse region. And so I shouldn't expect that they have invented anything new. They just don't really know what they're doing. And I'll explain what their experiment is. What they have in their experiment is two bar magnets. And they're using this really awful dipole magnetic model, which is the most horrible thing ever devised. It is so cartoonish, it's so Wile E. Coyote, it's so ridiculous. What I'm going to do is I'm going to translate those to the new magnetism model of magnets. The new magnetism model of magnets, basically you have this is the edge current here. And because that's north is toward the green, the edge current flow actually flows this way. And this edge current flows this way. Okay, and so I don't work with poles, I work with edge currents. Edge currents work the best. They're easier to use, they give you good answers, and you get rid of this silly B field abstraction, which I have seen people use. Well, I'm going to go off on a tangent here. And what's happening is they put a piece of graphite. I'm not sure if it's graphite or graphene, but this diagram from there says graphite, which would be like pencil lead. And that hovers in the middle here, and it stays in the middle because if they push it toward the end, this is actually looking in the end of this experiment here. So these magnets aren't that amazing. It's like the regular bar magnets, flat magnets that we use, except that they just rounded the edges of them. Now maybe that gives a wider edge current, I don't know. But when I use physics to simulate it, sorry, my printer is on the fritz here. I put two regular flat magnets, and I got the poles going the other way. It doesn't really matter. And then what I did is I put another magnet going the opposite way, kind of as a test. Okay, because this is going to be in repulsion in the orientation that it's in. So what's their force? And this is the orientation along. Z comes up out of the plane. X is, come on, dude. Really? Seriously? You're really that needy, huh? Come on, dude, over here. Come here. Come on. Come on. Good boy. Good boy. Very needy cat. Come on, you're blocking the light, dude. And then what I did is I moved that magnet along the top in the area about where they have their little piece of graphite. And the force going in the y direction, which would be up here, oh, I got their Camel Back effect, no problem. But the more interesting effect is the repulsion from the edge currents, these ends of the magnet. Well, as the test magnet goes toward negative x, there's a force pushing it toward positive x. And over here, as it goes toward positive x, there's another force that pushes it toward negative x. And that's what would keep the magnet in the center. Because this little dip in this little thing here isn't really that much. Now, don't go out and try to build this, okay? I'm using a magnet to simulate the magnetic repulsion of graphite. Okay, if you try to do this with a magnet here, you're going to get this magnet's going to have 2 newtons of force going up. This, oh, by the way, I use 14,000 amp neodymium magnets in the model here, and this is a 1,000 amp. What's that other material? Ceramic magnet. Okay, and that gives a 2 newton of force in the y direction. So if you actually try to do this with magnets, you're going to see this thing fly up and flip over and try to attract. And that's the magic of graphene and those things. So here's a time for a rant. The opening statement contains the crux of the problem. This is their opening statement, and I'm going to read it to you. Electromagnetism is a branch of physics that deals with all phenomenon. All phenomenon, really? As if we know all phenomenon of electricity and magnetism. This field is the key foundation of our modern age of electricity and information technology. It is governed by a set of fundamental principles encoded in 4 equations called Maxwell's equations. Again, a myth. Maxwell's equations are a subset of everything we know. They're not the full encoding of everything. These have been known for approximately 150 years. Every time we harness fundamental effects as prescribed or predicted by this theory, we reap immense benefits in terms of technological advantage. Gibberish, 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 gibberish. Things like electric machines, motors, various electronic devices, circuits, computers. This subject is actually considered classical physics, which seems to suggest that we have known everything we need to know about it. That means if this isn't predicted by Maxwell's equations, that means it must be something new that we didn't know in 200. My friends, when engineers or physicists graduate with a bachelor's degree from any university, they are not experts in Maxwell's equations. Not one. In college right now today, they basically give you maybe 1 or 2 course, just basically pass your brain over the book. You don't really become a master. You just kind of become familiar, and they pump a lot of dogma into you. Oh, Maxwell's great. And, they give you a couple tests that are easy to get the right answer, and you think you're a master. Okay, Maxwell's equations are not, they're horrible. Let's actually take a little look at Maxwell's equations. That was my rant. These are Maxwell's equations in point form. There's also Maxwell's equations in integral form, but they're pretty much the same thing expressed a different way. They predict the same thing. They're just a different form. Okay, now the problem with these 4 equations, it's a field in terms of another field. Okay, that's how Maxwell derived his plane wave equation. A field is supposed to be able to generate another field without any other medium or anything like that. But this doesn't tell you the forces on charges. It doesn't tell you how one charge affects another through the distance of space. Okay? For that, you need Coulomb's model. And with Coulomb's model, because it's a conservative field, you need Kirchhoff's law. And this is Kirchhoff's law in point form. Kirchhoff's law also comes in integral form. They pretty much say the same thing. And this is where I have heartburn with classical theory, because Kirchhoff's law in point form contradicts Maxwell's 4th equation. This says the curl of an electric field can only ever be 0. And this is saying a curl of an electric field can generate a magnetic field. Or, wait a minute, is that a changing magnetic field generates a curl in an electric field? That's another problem with these equations. I've seen people, what's the causality? Does this generate this or does this generate this? I've seen a lot of people use this either way as if it doesn't matter. Okay, so there's an ambiguity. There's an ambiguity of causality here. Okay, there's another problem here. Is this says that the divergence of an electric field, and why they have two different representations of electric fields and two different it's so ridiculous, it's so unnecessary. It's really unnecessary. Two different definitions of a magnetic field, two different definitions of electric field, really ridiculously unnecessary. But anyway, this says a divergence of an electric field gives you the charge contained, or the charge density contained, and that's wrong. Because if you have equal and opposite charge, you're not going to see a divergence. Okay, this is really the net charge, and that's another ambiguity. Okay, and the other problem here is that the electric field around a current density is d dt. So you can never separate the electric field of a charge from the charge that's moving. This is an oversubscription. I've derived this 3 or 4 different ways. And no matter what you do, you cannot separate the electric field from a charge. And so this is complete fraud. This should be one or the other, not both. And so this has been oversubscribed. Okay, and the derivation for this is in EMV002, the Great Displacement Current Caper. And I show you very, very clearly, a very, very simple derivation, that this is the same thing as this. You cannot separate them. Okay, but then there's more. You still need F equals QV cross B, because this is a charge moving in a magnetic field is going to curl. And this is the force on the moving charge in the magnetic field. There's no curl of velocity here. There's not one single velocity term here. Now maybe you can infer it from there somewhere, but why should you have to? Okay, then why? How do you know when to use this or this? It's ridiculous. Okay, and then you need to know how a magnetic field is generated. Here you get your electric field, here you get your magnetic field. Nowhere in here does it tell you. Okay, and then this is still missing a common experiment. The effects of a common experiment are not in here. That was one of the things I inferred to get that third term in new magnetism, or that middle term. And so, you know, so instead of going through all this crap, you could just use new magnetism, new electromagnetism. This is simple charge-to-charge effects boiled down. This is new. This is new induction. This replaces Faraday's law, which is ambiguous. And if you look real closely, you have F equals ma. You got Newton's law coming right out. And the minus sign is correct. Because when you apply a force to a mass, the inertial force acting is always opposite to the applied force. So this is inertia. And it's also the mechanism of gravity. You look in the foundation series, it's simpler. It is so simple, a school child can use this equation. And since I've gotten rid of all the ridiculous field abstraction, we don't know what the fields are. Okay, when we show that the magnetic field, and they put the bar magnet there, and they put the iron filings around and say, well, that's a magnetic field. Well, duh, iron filings affect a magnetic field. So this B field model that they came up with is not a magnetic field. It's how iron filing is affected by a magnetic field. And they've been tricked by their eyes. And this B field abstraction leads to so many problems that I've seen. Getting rid of it, and eventually with Ethereal Mechanics, we're going to hopefully replace it with something new. But for new electromagnetism, I just wanted to be able to get the effects that we can actually measure and see. Not the B field and the D field and the E field and the H field, which we can never see. The only way we can observe those is to put something in the way, and that's usually a charge. And so this boils down at least the known effects. I believe there's more than this, and this might actually be wrong. There's got to be something more. Something, the railgun there says there's something missing here. And that's what I'm trying to find. This is just trying to put it in pictogram for those people who don't like math. I have to make another video to explain these. Don't worry about these right now. And if you want to see the current model of new magnetism, there's a Distinti's, I forget what it is, D002 new magnetism part. I'll try to remember to put all the links in the low bar. But what's the silver lining here? The silver lining is graphite, or graphene. I don't know what they're using. They say they're using graphite. Because here's an interesting thing about diamagnetic materials. Classical theorists just say, oh, well, you know, it's got the mu relative. And that's negative for diamagnetic materials. And they think now, because they can assign a number to it, that they understand it. Okay? We're going to talk about this. I'm going to talk more about this on the Patreon side for Patreon members, because it relates to another link that I had put out last week. And we're going to talk about the interesting concept of this is the diamagnetic materials are the most amazing thing. And we're going to explain that. And I'm going to put out a challenge on the Patreon side. Okay, also Physics 1.0. We're going to release the source code to Patreon engineers and above. The reason it's not for general release yet is that there's not a general user interface yet. Okay, right now you have to know how to program in C# and you need a Visual Studio license, because what you're going to do, and then there'll be, you know, how-to videos published. Everybody be able to see how it works, and you'll see what's involved. There's not like, you know, a general user interface. I don't have the time to do that. Right now I'm just writing the software so that I can make a scenario and put stuff into the universe and then just run it through use the C# interface as the interface. And the reason why I'm releasing this now is because we're going to upgrade. I'm going to be upgrading physics to use new vortex algebra, so that we can try out these new things and these new vortex diagrams that we described before, and see if the new guess at magnetism, which I published on the Patreon side, if that follows all the magnetic experiments that we've seen. Okay, so that's where we're going. Thanks to all my Patreon people. Thanks for being patient. There's a lot going on. And we're going to end with the words of Mark Twain. Don't let schooling interfere with your education. Great words. Thank you very much.